Good morning to one and all. I'm G. Vamshi from branch of Tribly. Today's my topic was about uh, lead and lag compensator with complex poles and zeros. Design the formulas for modeling and loop shaping. In classical loop shaping, compensator structures are typically cased to modify the gain and phase characteristics of open loop frequency response. These alterations are used to achieve the closed loop performance specifications for disturbance rejection, reference following noise rejection, and gain and phase margins. Lead and lag compensators are standard tools employed in a loop shaping process. A lead compensator has transfer function C of S equal to root of P by Z into S plus Z by S plus P, where whose maximum phase phi suffix m occurs at frequency, and omega suffix m is equal to root of P into Z, equation 2, and P greater than omega m greater than Z greater than 0. The gain of equation 1 is unity at omega m. The maximum phase led pi omega of lead compensator is pi of m equal to C of omega m equal to C of plus Z minus Z omega plus m. And since 0 less than omega m by pi actually 90 degrees, the maximum phase led omega m is less than 90. Future more omega m, high m, and p and z are related by equation 2. And z by p equal to 1 minus sin phi m by 1 plus sin phi m. Figure 1 shows that both plot for a lead compensator with a maximum phase lead of 45 degrees at omega m equal to 1 radians. The pole has at p equal to minus 2.41 and 0 is at minus z equal to minus 0.41. Transfer function of lag compensator is reciprocal of lead compensator. Lead compensator are used to increase the phase margin for a given crossover frequency. Lag compensator are used to increase the low frequency gain for improved disturbance resistance or decrease high frequency gain for improved noise rejection or augmented gain margins. Lead and lag compensator are also used to modeling to the match again and phase futures frequency response data. For phase lead greater than equal to 90 degrees, multiple lead compensator must be cased together. In practice, phased lead compensator is also used for phase lead less than 90 degrees because of high frequency gain of single lead compensator with maximum phase lead by more than 60 degrees is significantly larger than high frequency gain of n cased compensator, each contributing 1 by n of the same total phase lead. Figure 2 shows the high frequency gain of single lead compensator functional of total phase lead. The simplest case is square of lead compensator called double lead compensator. The transfer function of double lead compensator which has maximum phase lead phi of m is C double S equal to C square S equal to P by Z into S plus Z by S plus P whole square. Omega y by omega n into S square plus 2 I n omega n s plus omega n square by s square plus 2 I n omega ds plus omega d square. Equation 5 where omega n to z omega d equal to p and I of n equal to I of d equal to 1. The poles and zeros of double lead compensator real and multiplicity of 2. The last expression in phi suggests variation of double lead compensator which has minimum polynomial second order by proper transfer function having damping ratios less than 1. In particular, complex lead compensator introduced in equation 1 various double lead compensator in which poles and zeros complex conjugate same damping ratio The transfer function has form C complex WP by WZ S square plus 2 of 2I of WZS plus W square Z by S square plus 2 I of WPS plus WP square. Equation 6 where WP is the underdamped natural frequency of poles and WZ is underdamped natural frequency of zeros, and the equal damping ratios I provide the symmetric phase peak. The gain of 6 unit in at omega n. Frequency is maximum phase lead. The maximum phase lead is designated to 5m notional simplicity in following development. The transfer function of complex lag compensator is the reciprocal of complex lead compensator. Figure 3 shows the board flat of complex lead compensator with damping ratio I of equal to 0.7, maximum phase lead 90 degrees. 1 radium compensator for comparison. Figure 3 also showed burst flat double lead compensator with maximum phase lead 90 degrees at omega 1 radian. Both plot figure 3 illustrates several notable difference between double lead compensator and lead compensator. First, phase peak of complex lead compensator sharper than phase peak double lead compensator. Next to magnitude region complex narrow than magnitude translation region double lead. Figure 1 was about both flat of lead compensator of equation where maximum phase is 45 degrees at m equal to 1 radian. The pole is at minus p equal to minus 2.41 and 0 is equal to at minus z equal to minus 0.1. Figure 2 was about high frequency gain root of p by z d. The single lead compensator equation 1 as function of its maximum phase lead pi of m. The high frequency gain increases non-linearly with increasing phase lead. The lead capacitor are often said with hazard in practice to reduce high frequency gain in desired maximum lead phase lead compensator. Furthermore, the ratio of high frequency gain assimilate low frequency gain assimilate is smaller for complex lead compensator than for the double lead compensator. Finally, the slope of magnitude frequency omega m is steeper for complex lead compensator than double lead compensator. The smaller ratio between high frequency and low frequency gain assume plates of complex lead compensator is advantage compared to double lead compensator, which complex lead compensator used to increase the phase margin for given 0 to dB crossover frequency of a narrow phase peak of complex lead compensator implies that a phase of complex is open loop attains 180 degrees crossover at lower frequency with using complex lead compensator than which using double lead compensator also rate which opens the magnitude drops above 0 to dB crossover frequency. Complex lead compensator for double lead compensator, the latter two features might be result to smaller gain margins or lower noise rejection, never 0 to crossover frequency 2. For complex log compensator, the steeper magnitude slope, narrower phase nodes are advantages compared to double lag compensator, while smaller difference between high frequency and low frequency gain is disadvantageous. Smaller frequency gain exemplars of complex lag compensator tends to reduce low frequency gain and decrease low frequency disturbance. Rejection compared to figure 3. Rejection compared to with double lag compensator, however, sleeper magnitude slope, narrower phase nodes mean complex lag can be applied to increase the rate at which open loop magnitude drops above 0 dB crossover frequency while changing minus 190 degrees crossover frequency very little while trading gain margin for phase margin. Complex lag compensator provide larger gain margin compared with double gain compensator. Another application for which complex lag similar advantage over double lag compensator to improve the performance single input single output SISO system have multiple 0 to dB crossover frequencies. Common lead and complex lag compensators are also useful for system modeling. The board plots and measured frequency response data often exhibits narrow phase peaks and not just complicated magnitude behavior in vicinity of peaks and notches. The compound layered complexes lag compensators can be used to replicate this board plot features in many cases. We provide simple closure from experience expressions from determining the transfer function parameters of complex lead and lag compensator for specified phase lead or lag at particular frequency of maximum phase lead lag. And for each compensator, we characterize the relationship between damping ratio and ratio of asymptotic gains and slope of magnitude plot frequency of maximum phase lead and lag with width of phase peak and width of magnitude transition region. And thank you. This PPT made by G. Vamshi.